Hi, we're now going to talk about cardiac output. So cardiac output is the amount of blood that the heart puts out in a given amount of time. Usually we talk about one side or the other, so we might say the left ventricle output is, let's say, 5 liters per minute. That would actually be fairly typical. Now, a question that sometimes comes up is, okay, if the left ventricle is putting out 5 liters a minute, what about the right? Isn't it weaker? And as it turns out, it's actually important that the two be the same. So let's take a look at why that is. So here's our left ventricle. Now let's imagine that this is putting out 5 liters of blood per minute, going out to the systemic circulation. So there's our 5 liters per minute going out here. Now, if we're putting 5 liters per minute into the systemic circulation, that kind of inherently implies that we're going to be getting back the same amount. If we're putting 5 liters into it every minute, if we're not getting 5 liters back every minute, then there's a leak somewhere. So let's assume that we've got 5 liters a minute returning to the right side, which means that our right ventricle is getting 5 liters of blood per minute. So if it's getting 5 liters of blood per minute, it had better be putting out 5 liters of blood every minute, or we're going to run into a problem. And let's actually take a moment to talk about what problem that might be. So let's imagine, oh, and by the way, it goes the other way too. Our 5 liters per minute going from the right means I get 5 liters a minute going into pulmonary, which means that I'm going to have 5 liters every minute coming back to the left side. So let's look at what kind of problem we might run into here. Let's imagine, for example, that we have a heart attack and it damages the left ventricle, so that the left ventricle can't push blood out as fast as it might. Now, if the right ventricle is putting out 5 liters per minute, then 5 liters is coming to the left ventricle. But what if the left ventricle can only push out 4? That if I'm getting 5 liters a minute, but I can only put out 4, I'm going to have a backup. So, for example, you might imagine, let's say someone gives me 5 M&Ms every second, but I can only pass on 4 M&Ms every second. What's going to happen to the M&Ms coming in? They're going to pile up. I'm going to get this buildup of M&Ms that I can't get rid of fast enough. Likewise, if my left ventricle is receiving 5 but can only put out 4, blood's going to start backing up in here. We're going to start building up blood in here. That's going to raise the pressure. And if you raise the pressure in the pulmonary circuit, you end up with some problems. For example, you end up squeezing extra fluid out from the blood vessels in the lungs. We'll talk about how extracellular fluid is made later. And that can actually end up causing a problem in the lungs, pulmonary edema, the buildup of fluid in the lungs, which makes it harder to oxygenate blood. That's a part of congestive heart failure. So damage to this side of the heart produces a backup and an increase in pressure in the pulmonary circuit. Likewise, damage to the right ventricle would mean that the right ventricle can't push out blood as fast as it's getting it, and blood would back up in the systemic circuit, causing an increase in pressure there. So that's why it's important that these outputs be matched to each other. Now that we know that, let's take a moment to talk about how cardiac output is measured. So we're going to say cardiac output. Let's see, what would go into knowing how much blood the heart puts out? Well, one thing that would go into it is how much blood does it put out on a single beat? So every time the ventricle contracts, how much blood comes out of it? We call that stroke volume, or SV. The other thing I'd want to know is how often does this happen? How many times a minute does my heart beat? Which is the heart rate. So we say cardiac output is equal to stroke volume times heart rate. Just to give you some typical numbers here, in a relatively young adult male, stroke volume might be 70 milliliters. How much blood can the left ventricle put out in one cycle? Maybe about 70 milliliters, which is roughly a quarter of a can of Coke, more or less. Maybe even a little less than that. So let's say about as much as I could easily hold in the palm of my hand, something like that. That's the amount of blood the left ventricle puts out into the aorta every time it beats. And if we figure a resting heart rate of 60 beats per minute, we would get a cardiac output of 4,200 milliliters per minute, which is 4.2 liters per minute. So a resting cardiac output, probably somewhere around 4 or 5 liters per minute in this person. Now that can change. In an athlete undergoing exertion, their cardiac output might climb to as high as 25 liters per minute. That's pretty big. That's a little more than a 5 times increase in cardiac output. So in that case, you've got the same amount of blood. It's just being pushed through both circuits a lot faster to make sure we get oxygen and supply it to the tissues. When you're exercising, you have much more need of oxygen, hence you need a higher cardiac output. But how are we going to get a cardiac output that high? If I'm looking to increase my cardiac output, I'm going to have to either increase my stroke volume or my heart rate, or both. To increase my I could increase my heart rate, but to get a 5 times increase in cardiac output, I would need to increase my heart rate by 5 times if that's all I was doing. A 5 times increase in my heart rate of 60 would make it 300 beats per minute, which is not really physiologically possible. So in order to get a bigger cardiac output, I'm also going to need to increase my stroke volume, how much the heart puts out on a single beat. So let's talk about what goes into stroke volume. Let's see if we can look at this using my bike pump here as a model system. So if I'm going to pump air with my bike pump, I lift the handle and I push it down. When I lift this handle, it brings air into the cylinder. And then when I push it down, it pushes that air out the cylinder, out through this hose. So how much air am I pumping? Well, let's imagine this situation. So I'm going to start my pump handle here. Now, if I raise the handle up and down and up and down, like this, take a look at how much air I'm pumping. When I go up and then down, I'm bringing in a certain amount of air, and then I'm getting rid of a certain amount of air. If I wanted to know the amount of air that I actually put out from the pump in this process, I could start by looking at the amount of air in the pump at the high point, and then subtract the amount that's left at the low point. The difference between them is the output of the pump, the amount that I actually pumped out. So how could I increase the amount of air that I'm pumping out? Well, if this is my normal high point, and this is my normal low point, I can do 2 different things. I could either make my high point higher. If I then keep the same low point, take a look at what I'm doing. Now I use a higher high point. Going down to the same low point, I'm pumping more air. You can see the difference here. Alternatively, I could use the same high point, but go to a lower low point. And again, going from here to here is pumping more air than I was before. Or I could do both, high and low, to get the maximum pumping. Of course, in the analogous in the heart is I could also do it either slowly. There's a heart rate of something like 60, maybe a little slower. Or faster heart rate means more air pumped, more blood pumped. In the cardiac cycle, the equivalent of the high point and the low point on the bike pump are things we call the end diastolic volume, which is EDV, and the end systolic volume, ESV. The end diastolic volume is the amount of blood in the ventricle at the end of diastole, so at the end of its relaxation, which means that will be the maximum amount. If we imagine a ventricle here, we'll have it. There's the atrioventricular valves, and there's the semilunar valves. End diastolic volume is what we get when that ventricle is at its maximal extent, when there's as much blood as possible in there. End systolic volume the end systolic volume is what you have left when that ventricle is at the end of its contraction. This would be saying that if this is my ventricle, as it expands, when it reaches its maximum, as full of blood as we can, that's the end diastolic volume. And then as it contracts, when it reaches its maximal contraction, whatever's left is the end systolic volume, volume at the end of systole. Those go into stroke volume. We say that stroke volume is the end diastolic volume minus the end systolic volume. The amount of blood in there at maximum minus this. So the difference between those is the amount we got rid of. That's the stroke volume. That goes into cardiac output. So really, we could add to this equation that stroke volume is end diastolic volume minus end systolic volume. So by increasing that or decreasing that, we can make our stroke volume bigger. We can then also increase our heart rate, and all of those together can make our cardiac output greater. So let's talk for a moment about what can change these things. End diastolic volume depends primarily on venous return. How much blood is getting back to the heart from the veins? So if my blood tends to pool in my veins, if it's not coming back to the heart well, that decreases my end diastolic volume, the amount of blood the ventricles have to pump. Thus, it will decrease my cardiac output. If I can change my end systolic volume by changing how strongly the heart contracts. So ESV depends on the contractile strength of the heart. That depends largely on sympathetic activity. Epinephrine acting on beta-1 receptors in the heart will make the heart contract more strongly, which will lower the end systolic volume. In other words, it'll have less left in the ventricle at the end of its contraction. Likewise, heart rate depends largely on sympathetic and parasympathetic activity. Now, just as an example calculation, let's erase part of it. If I have a person with heart rate of 70 beats per minute, end diastolic volume of, let's say, 135 milliliters, and an end systolic volume of, say, 65 milliliters. What is this person's cardiac output going to be? Here's how you do it. Cardiac output is stroke volume, which is EDV minus ESV, times heart rate. So cardiac output equals stroke volume, which is EDV minus ESV, times heart rate. That's 70 milliliters times 70 beats per minute. In this case, it'd be 4,900 milliliters per minute. Now, these are actually fairly typical values for EDV and ESV in a person at rest, at least a male person. The fact that typical has historically meant male is a problem. Maybe we'll talk about that a little later. But one thing that surprises people about this often is that that means that the heart only actually pumps out about 50% of the blood in the ventricle at rest. That's almost half of the blood that stays in there at the end of the contraction, which seems wasteful. But think of it as a reserve. That just means that in order to push more blood out of the heart, all you have to do is squeeze it a little stronger, and you can get more blood out and increase your cardiac output. Now, what's the relevance of cardiac output? Well, mainly, the amount of blood your heart puts out limits what blood you can send to your body. It also has a direct effect on arterial pressure. The pressure in the arteries is what pushes the blood out through the rest of the body. And that depends partially on cardiac output. So all else being equal, if you push more blood into the arteries, you'll increase the pressure, which means you'll get more flow through the rest of the body. Now, in a moment here, we're going to be talking about the relationship between pressure, flow, and resistance. So really, just as a preview, the amount of pressure in your arteries depends on the cardiac output, how much blood is going into the arteries, and what we call peripheral resistance, which is how hard it is for that blood to get out of the arteries and into the rest of the body. So this relates to that first part. Let's talk about that in the next part of the lecture.